Welcome to this lecture of the course Computational Hydraulics. We are in module 4 surface water hydraulics, and this is lecture number 4 of this module, which is unit number 4, steady channel flow and channel network. In our previous lecture class, we have discussed the problems for single channel and channel in series. What is the learning objective for this particular lecture class? To solve steady channel flow for channel network problem using implicit method. Again, we will be talking about the solution of nonlinear equation. This is not time implicit, this is implicit equation. Problem definition. In our problem definition to solution, in our previous lecture class, we have talked about a single channel. Let us say we have single channel, and we have also solved the case where two channels are connected. So, initial one was having milder slope, then we have a comparatively steeper slope like this, and there was junction point and single channel. In this case, the situation is that whatever flow is entering into the channel, we are getting same amount of flow here. So, in this case, our given discharge, for a given discharge, we can solve this problem, and only variable is y or flow depth. But if we have multiple channels, let us say that if we have this kind of situation where flow is coming from here and there are two channels in the downstream end. So, obviously, if the flow here is Q, flow there and the one section is Q2 and on another section is Q3, obviously this Q1 should be equal to Q2 and Q3. But we do not know the exact value of Q2 and Q3. It depends on the nature of the flow and the upstream or downstream conditions and junction conditions available within the channel network system. Problem definition, governing equation. Governing equation for channel flow can be written as boundary value problem. Again, we will be using same set of governing equations. So, continuity equation, momentum equation, but in our previous lecture class, we have not utilized this governing equation during our solution process. But in channel flow, again at any junction there will be multiple channels involved in the flow process. So, we can not exactly calculate or estimate the discharge value at the junction without solving this equation. So, what we will do, we will try to utilize the discretized form of both the equations and we will try to solve it simultaneously, so that we will have the solution for both y, that is the flow depth, and discharge for any channel network. Interestingly, in our last lecture class, we have considered NL plus one number of variables. That means, we have considered only y as flow variable. Now, if we introduce this Q discharge as another variable, then we need to solve 2 NL plus 1 number of equations. That means we need equations which will be coming, or discretized equations which will be coming from this continuity momentum, but these equations are applicable for segments. So, obviously we will get 2 NL number of equations here, and we need 2 NL plus 1 into 2, that means these many variables. So, extra equations we have to add to get the solution. So, for channel flow we have this general structure. We have our elevation head, flow depth, in this case velocity head or kinetic energy head. On the downstream end also we have our elevation head, flow depth, this kinetic energy head here, and this is the friction slope, which is the average one by considering the two friction slopes at 2 consecutive sections, I and I plus 1, and I is the segment number, XL which is the channel section our del x, and it is associated with the channel reach. For a particular reach we will consider a single value of del x. Now, as part of discretization we need to discretize the continuity equation for ith segment. If we discretize this equation for ith segment of Lth channel, then basically we are getting this for ith segment. We have any arbitrary case, L is the index for channel number, I is the index for different sections with channel reach. Now, in simplified form we have I for ith segment of the Lth channel, we have this equation. Now, we will not consider a constant value corresponding to this, and we are not going to solve the same set of equations that we have solved in our previous case. We need to consider these two terms as variables. So, we will not assign any value, or we do not have any value for our system. In functional form, I can just transfer this value on the left hand side. I can write this continuity Li, this is valid for 1 to NL number of segments. Now, again we can use the Newton-Raphson method, and for Newton-Raphson method, although this equation is linear, we need to calculate the coefficients or elements of our Jacobian matrix. Now, we have in each case, if we consider ith reach, let us say this is ith reach, and we have I and I plus 1, these two are sections. Now, in this case for section I we have variable L I and Q L I. On the right hand side we have Y L I plus 1, Q L I plus 1. So, all total for any segment will have 4 variables, 2 for depth and 2 for your discharges. Now, in this case if we have one equation, so we should get derivative terms with respect to these variables. So, if we have C L I equals to 0, this is our functional form, we should differentiate it with respect to Y L I, Q L I, Y L I, I plus 1, Q L I, I plus 1. So, first of all we do not have any y here. So, this is 0, Q L I, this is minus 1 because minus sign is there, Y L I plus 1, no Y I plus 1 term, this is 0, this is Q C L I del Q L I plus 1, this is 1 again because it has got a positive sign here. So, we have determined our coefficients for the Jacobian matrix for our continuity equation in this case. Now, again we need the discretization of our momentum equation. Now, to solve this momentum equation we can discretize it using a forward difference L I plus 1 and E L I, and we will take average of this friction slope in this case. In expanded form we can write this y z alpha q square 2 g a square L I plus 1 L I, these are the things we will get, and on the right hand side we have averaged form of S f. Now, from here we can get the functional form. Again we have these are variables, q is variable y L I plus 1, that is a function of y L I plus 1. So, these are variables. So, direct variable is y and q. Now, if we write this we need to consider the reverse flow situations. So, if the flow is in forward direction we will consider plus q, if it is in backward direction we will consider as negative q. So, if we use this square term here there will be loss of information. So, instead of using this square we will try to utilize this q L I plus 1, absolute value of q L I plus 1. So, obviously one term will get positive value, another term if it is positive or negative that will be considered during calculation process. So, similarly we can define the terms here. Now, outside we have only alpha L 2 g divided by 2 g N L square del x L divided by 2 So, in this case this term is not C1 and C2. So, these are not C1 C2 because we do not have q square term there. So, we can define two new terms in the next slide, but in this case as I have already mentioned, we have two NL nonlinear equations. So, NL number of equations which are corresponding to QLI or continuity equation, and NL number of equations which are corresponding to momentum, and this is corresponding to momentum equation. So, all total we have 2 NL plus 1 number of unknowns. So, in this case whenever we are going to take the derivative of this m, we should use this square terms only, because that absolute term that is not differentiable. So, if I write that the elements of the Jacobian matrix corresponding to momentum term, so we have these expressions. These are similar to the expression that we have already got for our channel in series or single channel case, but we have two extra terms here because we need to consider two extra variables in this case. So, we have this d1 and d2. d1 d2 these are constant terms, and these are corresponding to the lth channel, because alpha L, NL, delta XL these are parameters which are a function of or which are dependent on our channel reach. In general case, we already know that dr by dy we can calculate like this, where T is the top width, P is the weighted perimeter, R is hydraulic radius. So, this is the change in hydraulic radius with respect to y. dA and dy, this is dA dy and dr dy, both are functions of y. Boundary condition for subcritical flow, again we will consider that on the downstream end we will have the specified flow condition. So, this is the condition number 1, condition number 1, because we have considered NL equations in terms of C and M, and we have 2 NL plus 1 number of variables. So, if we subtract this, we need 2 more equations. So, what we can do, we can specify maybe discharge boundary condition at the upstream end. So, at the upstream maybe which is the channel 1, we can specify, this is for channel reach 1, and section 1 we can specify 1 1 equals to q, which is a specified q or q upstream value, and that will be the second condition, and we can solve this for our case. In this case obviously we have 4 terms, but these first two are 0 because we do not have any YL NL or QL NL terms. So, these are 0. Again we do not have any QL NL plus 1 term here, this is 0. So, only term is left is corresponding to YL NL plus 1. Now, we have all those equations there. Now, we can have other conditions within our system. If you have a channel network like we have discussed our channel in single channel or channel in series, we can solve this problem, but we need to specify our channel junction conditions. So, in this case in like previous one we have channel number L, L plus 1, L plus 2, L plus 3. Now, if we impose the channel conditions or channel junction conditions, we need to consider those conditions between this blue one, green one, blue one, red one. So, one condition is that the flow from left side should be equal to the summation of flow from the rightward, or if we consider this Jn or junction number 1 as general function, whatever inflow is coming to the system, that should be equal to outflow, and in this case we can have multiple channel junctions. So, in this case if we have another junction in the downstream portion, we need to specify both continuity and energy conditions. Energy condition means we need to see the energy balance condition between this section and this section and these two sections. So, obviously for any channel junction, if we have this 3 case or 3 channel case, we will have 1 continuity and 2 momentum. So, all total 3 conditions, because continuity is 1, because inflow and outflow values we need to consider, and 2 momentums or 2 energy conditions. So, in this case we need to consider energy between these 2, and again energy between this one and this one. So, all total for 2 junctions 6 conditions will be there. So, this is a general thing, mass conservation. So, channel discharge at inflow branch and channel discharge at the outflow branch, considering all branches, and energy condition neglecting the losses. If you have channel different channel elevation, then we should add elevation there, elevation term. Otherwise, we can directly consider the flow depth conditions. For junction, let us say that we have junction 1. For junction 1 we have this continuity condition, then we need to satisfy that energy condition there, and energy condition we have two conditions. So, out of this, because in every case we need to find out for any segment we need to find out variables, a phone number of variables or derivatives or Jacobian matrix term for 4 number of variables. In this case from our continuity 3 entries will be there. So, this is corresponding to NL plus 1, which is the end section of the channel L plus 1 L, and the first section of the channel L plus 1 and first section of the channel L plus 2. This was the case. So, this is NL plus 1 of LH channel, this is L first section of L plus 1 and first section of L plus 2. So, from next two equations we have two variables. So, 2 2 here 3 for these 3 equations we will get total 7 entries in the Jacobian matrix. So, corresponding to first continuity equation we will get 3 entries, for next two we will get 2 entries each. Similarly, for junction 2 we can expand this and write the elements of the Jacobian matrix. Now, in subcritical flow situation we have NL number of equations for our the segments, and NL number of equations from the continuity and momentum. Now, first one is from momentum, second one is from continuity, and if you have two boundary conditions, this is subcritical boundary condition at the downstream boundary, and at upstream boundary if you have specified boundary condition, then we can directly utilize that for the solution process. Now, with these conditions we have 2 NL plus 2, that means 2 NL plus 1 number of equations. Now, we can solve this system and we can get the solution for the problem. Solution for the problem. What is the structure? Structure is that for this matrix we have 4 entries. This blue one is corresponding to continuity, the red one is corresponding to momentum. So, at each segment, so this is let us say channel reach. For each channel reach L will have 1, 2 like that, I plus 1, they have ith segment. Now, in this case first entry corresponding to this segment will be from continuity, this is momentum. Now, for section I plus 1 or segment I plus 1, we have connections between I plus 1 and I plus 2. So, obviously, we need to consider the entries corresponding to I plus 1. If this is in general, we will try to write this variable as y1 q1, y2 q2, y3 q3. Like that, we will consider our variables. So, if we multiply y1 with the first term, q1 with the second term, y2 with the third term, and y4 y2 and q2 with the fourth term. So, that is the case. Again, for momentum we need to multiply the same variables or change in variables del q and del y, and for the next segment we need to shift our focus from these four entries to the next 4 entries. So, in next 4 entries these 2 entries will be common. So, these 2 entries are common, we will multiply it. So, obviously, in this case we will get the solution. These 2 are basically corresponding to boundary conditions, and if required we can incorporate the junction conditions. I have not shown those junction conditions within this matrix structure. Now, in this case we can again solve the problem that we have solved in our previous lecture class, that is channels in series. We will consider 2 channels, because in previous lecture class we have considered discharge as constant, but in this particular lecture class we are considering separate continuity equation during solution process. So, if we are considering separate continuity equation for the solution process, so we should get the same result that we have obtained using the single variable case. So, let us say that given information, first is channel cross section type is rectangular, B is 15 meters, G is 8.1 meter per second square, S naught 1 is 0.0004, S naught 2 this is S2 or bed slope for second channel. So, obviously, in this case we are considering a milder channel in the upstream and comparatively steeper channel in the downstream section. Next is N1, N1 is 0.01, N2 is 0.015, Lx1 is 100 meters, Lx2 is 100 meters, Q is 20 meters cube per second, and Yd is 0.6 meters required. They estimate the flow depth across the channels in series. Now, we are not changing any information in this one, only thing is that we are utilizing one extra equation during our solution process. Let us see how we can utilize that thing here. So, in this case I have considered the same code and changed that code for this problem. So, JUNC is the junction number, CHL is I have 2 channel reaches, QI is the 20 meter cube per second, this is a discharge at the upstream section, S naught this is for 1 and 2 0.0004 and 0008, N is 0.01, 0.015, B is this is 15 meters, G is 9.81, Lx for both the channel lengths this is 100 meters, YD in the downstream section we have 0.6 meters, M node which is 101 that I have considered here, and epsilon max this is for iteration we need 1 into 10 to the power minus 6, and global variable is B and G, because Q is again changing here, we are not considering constant discharge for this problem. So, in this case I have defined alpha first. So, alpha is 1 for both the channels. Now, I have defined this YV, YV is the variable and I should consider all the nodes and I should assign this initial value here YD into 1's sum m nodes. Sum m node that means 101 plus 101 202 nodes, this value will be assigned YV. QV again I need to assign initial value for this one, this is QI into 1's sum n node, that means 101 plus 101 total 202 nodes I have assigned this QV value. Now, in this case because this channel reach is there, this is for L equals to 1, this is for L equals to 2. So, starting from 1 to NL plus 1, again starting from 1 to this is N1 plus 1, this is N2 plus 1. So, these are the sections in between. So, in this case we have double index notation, that means L I, if I take L I that means it is representing the channel section in the Lth channel and for ith section. Okay. So, this is the local numbering, I need one global numbering for this one. What is that global numbering? I should use a global number that information I can utilize during the construction of Jacobian matrix. So, that global number is GID or global ID here. Now, I will start from ID value equals to 0. So, starting from L equals to 1 to CHL, that means for all channel reaches, and 1 to M node. M node means 1 to N1 NL plus 1, all nodes I should assign IDV equals to IDV plus. Whenever I am entering into this loop, I am adding IDV equals to IDV plus 1. So, GID equals to IDV, that means one by one I have assigned a serial number against each of those sections in different channel reaches. So, I will have unique number for any channel section in a particular channel reach. Now, here after assigning this one, so this is in this structure that if I have this structure which is L I should get one value. So, for different values of L I will get G I D. So, let us say L 1 I 1 I am starting from 1. In our case, if L equals to 2 and n node equals to 101, that means for the second reach or channel reach and 101 node, my GID should be 202, because I have considered all the nodes or all the sections during my this assignment process. Now, initial value, I have assigned initial value for individual variables y, v, q, b, but during my solution process I will have only one variable. Let us say that A phi equals to R equation. In this case I have j into del phi, because change in that variable is required. So, this is my right hand side, something is there, but in this process this del phi, it considers both y and my q values, and they are arranged like this: y1 q1, y2 q2, and all are del values. So, in a single calculation process I cannot use two different vectors y and q. So, I need one global vector for this definition. So, for this global vector definition, this what I am writing, this 2 into GV, this GV is a general vector or general variable in this case. So, general variable, what I am doing, I am assigning GID. So, if my assignment of GID, this is ranging from 1 to 202, 1 to 202. Now, this one is valid for y, v, which is y value, and q value, but in case of GV, which contains both y and q, so I need 404, that means 202 into 2 number of variables. So, for that one, if I take any general GID, so if I take any general GID for Lth segment and Ith section, and if I multiply it with 2, I should get the index corresponding to q, because I am arranging the variable like this: q1, y1, y2, q2, y3, q3, y4, and this is y4, q4. So, if my GID for L I for any arbitrary section or any arbitrary section in this case is 2. If GID equals to 2, that means GID into 2, that means 2 into GID is 4. That means I am considering the fourth term here. So, what is my fourth term? fourth term is Q2. So, all event terms are discharge terms. Now, if I take 2 into GID Li minus 1, this is 3. Now, 3 means this one. So, all odd terms, these are corresponding to flow depth values, and even terms, these are corresponding to discharge values. So, with this assignment, with this initialization, because initial values I can transfer here. Now, after that I can define the channel reach dependent parameters. Now, channel reach dependent first parameter is del x L. So, which is Lx divided by m node L minus 1 and d1 d2. In this case, the difference with C1 C2 compared to our previous lecture class is that we do not have any q square term here. So, in this case again we can get the z values here. This is our area calculation, we are considering rectangular channel, dA by dy r dr by dy calculation, and this is ml I. I have not written that CLI, because CLI the coefficients are either 1, minus 1 or 0. So, I have directly assigned those values. So, these are similar to our previous one, our previous definition. The only difference is here is that we need to transfer this d1 d2 values. We need to transfer del x s naught y1 y2 y1 q1 y2 q2 yq, in this case also yq. This is for m l I, which is for ith segment of the lth channel reach. This is del m by dy, which is the coefficient for L I, and L I, this is dm by dy, dm by dy, this is L I, this is y I, this is L I, this is y I plus 1. So, this is y I plus 1, this is y I, this is m, and now we need dm L I, this is dq I plus 1, and the term which is dm by Li by dq, this is for I L I. So, this term is here. Now, after defining these terms, we can start defining our Jacobian matrix. Initialization, I can start. Initialization is with this A zeros 2 into some m node. That means, if we have total 202 nodes, 101 plus 101. So, obviously, we have 404 variables. So, 404 into 404 should be the size of A. and R, the size of R should be 404 into 1. In this case, this count is 0, RMSE is 1. We have already initialized the GV or general variable there. Now, in this case what is happening, initially we have written this RMSE and we are starting with equation number 1. So, first equation is our upstream boundary condition, because we will have entry for 1 2, this is y1 q1 y2 q2. So, if y1 if our q1 value is specified, which is q directly, we can say that this is q1 minus q, some upstream location, and for that qv what is required? We need to differentiate it. If we differentiate it, we will get only second term, that means A11 is 0, no entry for A11. This is valid for section only. So, we will have only 2 terms associated with it, but the first term A11 is 0, but A12 this is 1, and right hand side we need to write that upstream boundary minus. So, if we write that upstream boundary minus, this means q1 minus q upstream here, that is what I have written here. Now, after that we can enter into this equations corresponding to segments. For equations corresponding to the segments, we have L equals to 1 to channel number, then I equals to 1 to m node minus 1. M node minus 1 means that I am considering Ln number of segments, NL number of segments for each channel. So, in this process I am considering 2 into NL number of equations. I have already considered 1 there. So, I need one more extra, so that I can complete 2 NL plus 2 number of equations there. So, A whenever we are entering into the system, before this continuity equation I am increasing this equation number equals to equation number plus 1. A eqn is 2 GID Li minus 1, that means whatever may be this Li value, I will have one unique ID or GID for my case, and in that case if I consider that 2 GID Li minus 1, that is the thing. Now, in this case another way I can represent it, what is that? That is nothing but we have this a L plus 1. Now, again I can consider that this is corresponding to our flow depth yi, this is corresponding to qi, this is yi plus 1, this is qi plus 1, because we are considering even numbers here, even numbers, because I plus 1 I plus 1 thing we are considering, this is GID L I plus 1, this is GID L I plus 1, 2 into, but 1 minus 1 is here, minus 1 is here. So, these are corresponding to y values. Now, in this case again we can avoid this and we can write it in general terms. So, this is the case where we have for any this Jacobian matrix will have equation number corresponding to that equation number will have entries. So, first entry, that is corresponding to 2 into GID Li minus 1. Next one is GID Li, that means this is corresponding to y, this is del I and this is del q I, this is I, and this is corresponding to del y I plus 1, and the fourth one is corresponding to del y I plus 1. So, in this process we have generated these equations, and the first equations are basically these are continuity equations. That is why I have not written the coefficients separately, because we have 0, minus 1, 0, plus 1 terms here, because we have q I, this is corresponding to L I plus 1 minus q L I, this is equal to 0, and if we differentiate it with respect to these two variables, obviously plus 1 will be the coefficient of this one and minus 1 will be the coefficient of this one. So, this is minus 1, this is plus 1 here. Now, we have completed our continuity. Again, after completing this continuity, again we need to add this eqn. For eqn, again we will be adding one momentum equation. For momentum equation, we have to utilize this GID Li and GID Li plus 1, these two segments or these two sections for a particular segment. Now, with this we can calculate our thing. Next thing is we need to specify certain junction conditions. Why these junction conditions are required? Because in this case we have only one condition, that is I have 1 and 2, this is my 1 or channel 1 and 2, these are connected from 101 node to 1 in the second channel. So, that is why junction information is 1, 2, 101, 1. Now, again I need to add one continuity equation here and one condition here. So, if I add these conditions, because the first term just junction information, I have junction information I or 1, this is the 1, the first channel, this is corresponding to L, second one is I. So, and third one is I, junction condition for third, that means the location of the end section, this is 3 and that means 101. So, with this information, if I run this, so obviously we have this equations. So, we have the condition for steady series or channel flow in series. Now, in this case we are getting one transition at this level. Again we need to transfer these values, all odd values we need to transfer to y, and qv values directly to or in this case this is update values, because we need to update values after solution of del q del yq. Del yq we need to add with gv values. Gv is the assigned initial value. After every iteration this is getting updated, and after we are getting updated values, we need to update y and v, because during calculation we are using this y and v values. So, in this case we are directly getting the solution. So, obviously it is similar to our previous case. This is the channel transition. In this case, so obviously color is different, and we are getting one transition here. So, with this approach we have solved both discharge and continuity equations for both the problems. Now, we have all total junction conditions, boundary conditions, and if we utilize those information, we can directly get the solution out of this. So, this is the estimation of flow depth across the channel, and we have solved this problem. So, this is with rectangular cross section we have solved. So, code is channel steady 1D channel network SCI. So, you can utilize this code to check the solution process. Thank you.